Welcome back, everybody. Dr. Rhett Smith for ProtonGuru.com, going over lesson 6.11 now. And the topic of this lesson is doing nucleophilic acyl substitutions where we use an oxygen-centered nucleophile to react with carboxylic acids and esters. Now, in lesson 6.10, we talked about how we could take the OH on the carboxylic acid and replace it with a chlorine. Because the OH group on a carboxylic acid is kind of acidic, it can cause problems with some nucleophiles. Well, you don't always have to take the OH of the carboxylic acid and convert it to a good leaving group before you can do a nucleophilic acyl substitution. One strategy you can use is called acid-catalyzed esterification. The name kind of suggests you're going to make an ester, and this is often called Fischer esterification. Well, you're going to add an acid catalyst. And if you look way back to the beginning of our discussion of carbonyls, we learned that if you add an acid, it can protonate the carbonyl oxygen to make that group much more reactive to nucleophilic attack. And that's exactly what happens in the presence of an alcohol. So addition of the alcohol leads to this species. There's your intermediate. Now, a lot of times you'll see people just write B for base. This could be another equivalent of the alcohol or some water in solution. As you'll see, we'll make some water in the course of this reaction. Some sort of proton acceptor with a lone pair to take that proton off. That'll get you to the species in box A. And I want to point out that all these steps are actually reversible as indicated by these equilibrium arrows. So we can push this reaction either way. So what could happen to this species? Well, we've got acid catalyst floating around. We could go back to this step where this group got reprotonated, but that's not productive in the forward direction. So what I want to show you is that the H plus floating around could also react with one of these two OH groups. Let's just say we have attraction of the lone pair on this OH to that proton. Then we'll get to this species, right? We're continuing from the top line here. And then what we can have happen is say, well, this H2O plus, if it leaves as water, would be a nice stable molecule. To get that to happen, we need to make a double bond from an O to the carbon, so the carbon doesn't have fewer than the 4 bonds it needs for its octet. That will get us to a species that looks like this. Now this looks almost like an ester, except the double bond O is still protonated up here. So again, one of these bases could be water or something floating around the solution, any proton acceptor. Take the proton off and make this ester. So the net result, if you think about it, is that the carboxylic acid reacting with an alcohol, reacting with just a catalytic amount of acid. And it's okay to be catalytic because we use it and then we get a proton back, and then we use it and we get a proton back over and over again in the solution. But you need a little bit of proton to get the reaction going in the first place to do this protonation. But if you take the alcohol with catalytic acid, with the carboxylic acid, eventually you will get the ester in this Fischer esterification process, where the OR group comes from whatever alcohol you add. You may remember another instance where we talked about reactions of carbonyls with all these reversible steps. These are the reactions of aldehydes and ketones with alcohols to make acetals and ketals, or the reaction of aldehydes and ketones with amines to make imines or enamines. Now, if you want to review those reactions that I'm talking about here, these are in lessons 6.6 and 6.7. We talked about these in our videos. And the idea is, if we have a reaction where every step is reversible, that means we can reach an equilibrium for any of these steps. Well, we can apply Le Chatelier's principle. Le Chatelier's principle applies to any equilibrium process. So a quick statement of Le Chatelier's principle here could be that an equilibrium shifts to consume excess or replace scarce compounds. So this means that Ester Hydrolysis, the reverse of a Fischer esterification, could also be accomplished. We need to push the equilibrium back away from the ester. Let me show you what I mean. Let's say we start with the ester, and we know there's a pathway that shuttles between a carboxylic acid and an ester, depending on which way we push the equilibrium. Well, if we want to take the ester and get rid of it, we need to use one of the compounds that would react with the ester in the reverse direction. So we say, well, what compound would that be? Well, in the forward direction, we're using an alcohol to put the OR group on. If we look in the backwards direction, we have water produced as a product of making the ester. Well, if we want to get rid of the ester, we add a bunch of water. So the water nucleophile will be what attacks the ester. And you'll need this acid catalyst to protonate the O to get this reaction going. So if I have a catalytic acid in excess of water, I will actually favor the right-hand side, as drawn here, of the equilibrium. So this is called Ester Hydrolysis, or acid-catalyzed ester hydrolysis. And we'll be able to make a carboxylic acid from the ester this way. We show you the pathway for that in the primer as well. Now, what if we want to favor the ester? Well, when you make the ester, you make some water. So we could make the water scarce by distilling it away. Remember, the equilibrium will shift to replace scarce compounds. So one thing we can do is do a distillation away of the water. Another thing we can do is just add an excess of the alcohol, right? The equilibrium will shift to consume the excess of that alcohol. Every time you consume an alcohol, one OR group from the alcohol goes on to the ester. So we could start with the carboxylic acid, like I showed in the previous page, and get the ester by using an excess of the alcohol, again in the presence of catalytic amount of acid, and this would be the Fischer-Esterification reaction. Now we can also use a base catalyst to accomplish the transformation of an ester to a carboxylic acid. And this is pretty easy to envision, that you could take an hydroxide anion and push the minus charge up to the oxygen. And what you've accomplished is making a pretty unstable alkoxide anion here. But you can push these electrons down and remove this OR group, temporarily making another alkoxide. Of course, this OR group is a strong base, and we've made an acid. So of course what happens is the alkoxide will deprotonate this, if it survives and doesn't have a reaction with water or something in between. So the products will not be carboxylic acid with basic conditions. You'll have deprotonated the carboxylic acid to make the carboxylate. You'll see that I draw this arrow as being non-reversible. A nucleophile of any type will be repelled by the negative charge on this oxygen, and this species will not want to accept additional electrons, being an anion already itself. So this is a way to make a carboxylate from an ester. Generally, you could add acid at the end to isolate the carboxylic acid if that was your end goal. Now, if you think about it, we can simply change this nucleophile from an OH to an OR. Say, well, what's going to happen here? We're going to have a very similar looking intermediate species, but instead of the OH that has attacked here, we've used an OR minus, so we have an OR. What's going to happen then is that if we push off the OR group that was already there, the net result would be that we've taken one OR group off and put a different OR group on. So we can take one ester and make it into a different ester. And again, you'll usually use water or something to neutralize this as it's formed. And this is a process called Transesterification, when you take one ester and make it into a different ester. Now this process uses a very basic nucleophile. The alkoxides are quite basic species. You can also take one ester and make it into another ester by a transesterification process if you use an acid catalyst. And this will look very, very similar to what we saw for the Fischer-Esterification. We'll just talk through this quickly since we've already seen that process. We start with an acid catalyst to protonate the OH on the carbonyl. Then we use an alcohol. So we have an OR group. If we deprotonate this group that we've just added, we get a species like we see in box A. Now, in order to progress to this species here, we're going to need to protonate, since we have acid catalyst, the group we want to leave. Now, we could protonate this group we just put on. That would go back to that species. So these are reversible reactions. But an alternative would be to protonate this oxygen, which is what we're going to do here. So to draw that arrow pushing step, we're going to draw this. And now you see that we have an HOR group with a plus on the O, and I'm showing it leaving. So what we're left with is a species that looks like this, with a positively charged O, and it looks almost like an ester at this point. We just need to deprotonate this O, and we get the ester. And the net result is that we've taken one ester that has this OR group here, and we've reacted it with, to push all the equilibria forward, let's say an excess of a different alcohol, an alcohol bearing a different R group than this had. So R prime is different from R. That's why we have a different little symbol. And we have a catalytic amount of H+. And what we get is the HOR, came from this OR prime, and the OR group from this alcohol that we added in excess has replaced that OR group. So we took one ester, made a different ester. Those are always called Transesterification. And this was acid catalyzed because we need the acid to get this thing kicked off. So this shows you a bunch of ways that you can take a carboxylic acid and make it into an ester, or you can take an ester and make it into a carboxylic acid, or you can take one ester and make it into a different ester, just by using appropriate acid or base catalysts and appropriate water or alcohol nucleophile.